Hello everyone, my name is David Perry, and I will be presenting our research on physics-informed learning-based attack analytics for electric vehicle charging management systems. This work comes from the Analytics for Cyber Defense Laboratory at Florida International University and the Center for Cybersecurity at the University of West Florida. As electric vehicles become increasingly prevalent, we're witnessing a fundamental transformation in how our power grids operate. However, this transformation brings a host of new cybersecurity challenges that we must address proactively. To begin, I will start by outlining why this research is critical. Power grids are constant targets of cyber attacks. One particular case is California's grid operator fending off millions of attacks each month, and the integration of electric vehicle charging stations creates additional attack surfaces that malicious actors can exploit. Specifically, false data injection attacks can manipulate charging parameters, resulting in altered power profiles that affect the entire grid stability. Now, these attacks are particularly concerning because they can operate stealthily while causing significant disruptions. The key challenges we face include limited access to operational models for testing, ethical constraints that prevent real-world attack experimentation, and the fact that traditional computational models fail to capture the complex dynamics of these cyber-physical systems. Most importantly, we need real-time vulnerability analysis to protect our increasingly electrified transportation infrastructure. Our research addresses these challenges through three main contributions. First, we developed a novel physics-informed neural network-based attack analytics model. This approach overcomes discretization limitations by exploring the continuous attack space without predefined assumptions, giving us a more comprehensive view of potential vulnerabilities. Second, we implement gradient-based optimization that identifies attack vectors capable of maximizing performance deviations while avoiding computational overhead. This allows us to find the most damaging attacks efficiently. Third, we incorporate physics-informed constraints that ensure our identified attack vectors remain realistic and actionable, significantly reducing false positives. Our approach provides direct solutions to ordinary differential equations, enabling more efficient and accurate attack modeling compared to traditional discretization methods. Now, let me explain why physics-informed neural networks represent a significant advancement over traditional approaches. Traditional methods rely on numerical solvers that require discretization of the temporal domain. They must solve problems step by step, sequentially, making them computationally expensive for complex systems like EV charging networks. In contrast, our PINN approach embeds physics equations directly into the neural network architecture. This eliminates the need for discretization and works in the continuous domain. Most importantly, it enables parallel computation and learns solutions across the entire domain simultaneously. Our performance comparison demonstrates dramatic improvements. For a 5-station network, our PINN model requires only 18.3 minutes compared to 30.5 minutes for traditional solvers. For larger 15-station networks, the difference becomes even more pronounced. 60.5 minutes for PINN versus 213.2 minutes for traditional methods. This represents more than a 3 times improvement in computational efficiency. Our PINN architecture uses an LSTM-based structure with 4 hidden layers and 512 LSTM units per layer. It is specifically designed to capture nonlinear and time-dependent behaviors. The loss function incorporates 3 key components: power flow loss, voltage regulation loss, and EVCS dynamics loss. Our attack technique focuses on false data injection attacks against EV charging management systems. The mathematical formulation shows how attack measurements can be expressed as perturbations to normal voltage and current readings. We make 4 key assumptions about attacker capabilities. First, attackers have extensive knowledge of control algorithms, network parameters, and anomaly detection thresholds. Second, they have selective access to voltage and current measurements, but not control signals. Third, they can operate under variable load conditions. And lastly, they maintain sustained access for continuous monitoring and manipulation. Our optimization framework maximizes the deviation between attacked and nominal system states, creating the most disruptive scenarios while remaining undetected by existing security measures. We validated our approach through both simulation and hardware testing. Our simulation environment uses an Intel Xeon processor with dual RTX 4090 GPUs and 258 gigabytes of RAM. Testing was done on an IEEE 33 bus grid with Simulink-based EVCS model integration. For hardware validation, we built a physical testbed using Arduino controllers, DC-to-DC regulators, various current and voltage sensors, a Raspberry Pi, and the Steve charging management system. We implemented the OCPP 1.6J protocol via WebSocket connections and conducted attack testing using Kali Linux, Wireshark, and man-in-the-middle techniques. Our hardware results demonstrate real attack impacts. Voltage dropped from 14.11 volts to 12.8 volts. Current decreased from 1.56 amps to 1.09 amps. And power consumption reduced from 22 watt-hours to 14.1 watt-hours. These results validate that our simulated attacks translate to real-world effects. Our experimental results answer 3 critical research questions. What is the impact of attack vectors on the charging schedule? How scalable are attack vectors for creating disturbances in EVCS networks? And how computationally efficient is the PINN-based model compared to traditional methods? This figure shows the results of the PINN model for calculating the optimal attack value for voltage measurements, EVCS output voltage, EVCS output current, and active power delivered by EVCS, all while targeting at most 9 EVCS. As you can see, the system's progressive deviation under these attacks lead to voltage instabilities, power flow shifts, and cascading failures. For scalability, we successfully extended our attack analysis from 5 to 15 EVCS stations. We observed progressive voltage instabilities that cause cascading failures while maintaining stealth. Our system can automatically identify vulnerable bus locations in the network. Regarding computational efficiency, our PINN-based model demonstrates superior performance compared to traditional methods, with the efficiency gains becoming more pronounced as the network size increases. Negative impacts include charging schedule disruption. We found that cyber-physical attacks can extend charging times up to 7 times longer than normal by manipulating charging management system set points. This creates severe operational disruptions. Power reduction would lead to grid congestion, and system instability would arise from voltage regulation errors. Economic losses would arise from extended charging times, and degraded user experience would arise from unpredictable schedules. Safety risks are equally concerning, including thermal stress from over-delivery scenarios, battery degradation, overall system reliability threats, and potential cascading failures with network-wide impacts. Our key achievements include developing a novel PINN framework for EVCS vulnerability analysis, enabling continuous and scalable attack vector identification, demonstrating superior computational efficiency versus traditional methods, and providing real-world validation through our hardware testbed. The research impact is significant. We've overcome discretization limitations, enabled real-time vulnerability assessment, provided a physics-aware security framework, and supported enhanced EVCS resilience strategies. Future research directions include exploring broader cyber-physical attack scenarios, developing robust mitigation strategies, establishing resilient design principles for smart grids, and integrating advanced defense mechanisms. This work positions physics-informed neural networks as a robust foundation for developing physics-aware defense mechanisms to protect increasingly complex power grid systems against sophisticated cyber threats. So in conclusion, as we move toward an electrified transportation future, understanding and mitigating cybersecurity risks in EV charging infrastructure becomes critical. Our PINN-based approach provides both theoretical framework and the practical tools that are needed to build more secure and resilient charging networks. Thank you so much for your attention.